Definition, syntax, and memory allocation of struct versus union. What they are: both struct and union are aggregate types in C and C-like languages. A struct groups several values together, each with its own storage. A union also groups several values, but all members share the same storage. Only one member can hold a valid value at a time. Syntax: struct point, open brace int x semicolon int y semicolon close brace union number open brace int I semicolon float f semicolon double d semicolon close brace. The keyword tells the compiler which rule to follow. After the closing brace, you may optionally give a tag the name after struct or union and/or a typedef. Memory allocation analogy: think of a struct as a mailbox with several separate slots. Each slot is a different letter. A union is like a single slot that can hold only one letter at a time, but the slot is big enough for the biggest possible letter. Struct point reserves space for x plus space. For y, if int is 4 bytes, the struct occupies at least 8 bytes plus any padding discussed later. Union number reserves space equal to the largest of its members. If int is 4 bytes, float is 4 bytes, and double is 8 bytes, the union occupies 8 bytes, and any write to I, F, or D will overwrite the same 8-byte region. When to use which: use struct when you need all the data simultaneously, for example, a point with both x and y. Use union when you need to store different representations of the same concept, but never at the same time, for example, a token that can be either an integer literal or a floating point literal. 2-point size determination rules, including padding, alignment, and size of calculations. Alignment requirement: every type has an alignment A of t. For most CPUs, a 4-byte int must start at an address that is a multiple of 4. The compiler may insert padding bytes so that each member respects its alignment. Struct size layout proceeds member by member. After placing a member, the next member starts at the smallest address greater than or equal to current address that satisfies its own alignment. After the last member, the compiler may add tail padding so that the total size is a multiple of the struct's largest alignment. This enables arrays of the struct to keep each element correctly aligned. Mathematical expression: size of struct equals roundup of open parenthesis sigma size of member I plus sigma padding I close parenthesis comma max alignment. Struct s open brace newline char c semicolon comment size 1 comma alignment 1 newline int I semicolon comment size 4 comma alignment 4 newline short s semicolon comment size 2 comma alignment 2 newline close brace semicolon. C at offset 0. 3 bytes padding to reach offset 4 for I. I occupies bytes 4 to 7. S wants alignment 2, so it can start at offset 8, already multiple of 2, no extra padding before S. Tail padding: largest alignment equals 4 current size 10 round up to 12. Size of struct S equals 12. Union size: the size of a union is the size of its largest member rounded up to satisfy the union's own alignment, which is the maximum alignment among its members. No internal padding between members because they all start at offset 0. Union U open brace newline char c semicolon comment 1 byte comma align 1 newline int I semicolon comment 4 bytes comma align 4 newline double d semicolon comment 8 bytes comma align 8 newline close brace semicolon. Largest member is double 8 bytes alignment, 8 already satisfied. Size of union U equals 8. Size of operator size of is evaluated at compile time. It returns the size including any padding expressed in size t. Size of on a pointer gives the address size, usually 8 on 64-bit 4 on 32-bit, independent of what the pointer points to. Why padding matters: misunderstanding padding can lead to bugs when you serialize a struct, for example send over a network, because the receiver may interpret the padding as data. Use pragma-pack attribute packed or manual bytewise operations when you need a packed layout, but be aware that misaligned accesses can be slower or even cause hardware faults on some architectures. Explanation 3. Field access semantics and type checking constraints for members of struct and union. Reading a member struct, always safe. The member has its own storage. The value you read is whatever was stored there last, or an indeterminate value if never written. Reading a member union, safe only if that member was the most recent one written. Reading a different member yields an implementation defined or indeterminate value, often called type punning. Writing a member struct. Writes affect only that member's bytes, other members stay unchanged. Writing a member union. Writes overwrite the whole shared storage. After a write, the active member becomes the one you just wrote. Type checking struct. The compiler knows the exact type of each field. You cannot assign a float to an int field without an explicit conversion. Member of pointer operator arrow struct. Works the same for both. You first have a pointer to the aggregate, then ptr arrow member. Member offset struct. Each member has a different offset obtained via offset of struct member. Union offset union. All members have offset 0. They start at the same address. Struct is like a drawer with labeled compartments. You can open any compartment and see what's inside without disturbing others. Union is like a single compartment that can hold a book, a magazine, or a newspaper, but you must remember what you placed there. Pulling out a magazine when you had stored a newspaper will give you garbled pages. The C standard defines a stored value for each object. For a union, only the bytes of the active member constitute a stored value of that type. Accessing a non-active member is not undefined behavior per C. The result is implementation defined if the representation can be interpreted as the other type, but many compilers allow it as a way of type punning, subject to strict aliasing rules, see later. For dot initialization and assignment behavior differences, designated initializers, shallow versus deep copy. 4.1 Designated initializers. Introduced in C99, they let you initialize specific members by name, regardless of order. Struct person open brace new line char star name semicolon, new line int age semicolon, new line double height semicolon close brace. Struct person p equals open brace dot age equals 30 comma dot name equals quote alice quote close brace semicolon height becomes 0.0 automatically. For a union, you can initialize only one member because the others share the same storage. Union value open brace new line int I semicolon, new line float f semicolon close brace. Union value v equals open brace dot f equals 3.14 f close brace semicolon, the active member is f. Attempting to initialize more than one member in a union is a constraint violation, compiler error. 4.2 Assignment. Struct assignment copies the entire object bytewise shallow copy. If a member is a pointer, only the pointer value address is copied, not the data it points to. That is why we call it shallow. Struct s a equals open brace dot ptr equals malloc open parenthesis 10 close parenthesis close brace semicolon struct sb equals a semicolon b dot ptr points to the same memory as a dot ptr. Union assignment also copies the whole storage area, the size of the union. After the copy, the active member of the destination becomes the same as the source. Union UU1 equals open brace dot I equals 42 close brace semicolon union UU2 semicolon U2 equals U1 semicolon U2 now holds the integer 42 as its active member. Because a union's bytes are copied indiscriminately, you may unintentionally copy garbage from a previously active member if you forget to set the new active member. 4.3 Deep copy considerations. Neither struct nor union provides automatic deep copying. If you need deep copy, for example duplicate the memory a pointer points to, you must write a custom copy function. Struct vec open brace new line int star data semicolon new line size t lens semicolon close brace. Struct vec copy underscore vec open parenthesis const struct vec star src close parenthesis. Open brace new line struct vec dst semicolon new line dst dot len equals src dot len semicolon new line dst dot data equals malloc open parenthesis dst dot len times size of int close parenthesis semicolon new line mempy open parenthesis dst dot data comma src dot data comma dst dot len times size of int close parenthesis. Semicolon new line return dst semicolon close brace. 4.4 Summary table. Operation struct union designated init. Struct can initialize any subset of members, others become 0. Union must initialize exactly one member, the active one. Assignment. Struct performs bitwise copy of whole object shallow. Union performs bitwise copy of whole storage, active member after copy matches source. Deep copy support, none automatic, need custom code for both struct and union if members hold pointers. When a struct contains a union, a common pattern, initialize the union inside the struct with a designated initializer. And remember to set a tag, an extra enum field that tells you which union member is currently valid. Explanation: 5 space-time trade-offs in algorithmic problem solving. For example, storing multiple representations versus single active value. Store both matrix and list in a struct to allow fast edge lookup, big O of 1, and fast iteration over neighbors, big O of k costs, big O of v squared plus e memory. Store only one representation at a time in a union. Switch between them when needed, for example during preprocessing. Saves memory, big O of the maximum of v squared and e, but incurs conversion time. A struct token with a char pointer text and an int value wastes memory because a number token never needs the text buffer. A union token value that holds either int value or char pointer text. The surrounding struct token, with an enum type and union token value v, uses only the space needed for the actual kind of token. Struct rational with long numerator, long denominator, and double approximation keeps all 3 forms. You can switch quickly between exact and approximate calculations at the cost of 24 extra bytes per object. Union rational with a nested struct containing long numerator and long denominator called exact, and a double approximation stores only one representation. Suppose you need to store n equals 10 to the 6 numbers, each of which can be either an int 4 bytes or a double 8 bytes. Struct mixed with int I and double d has size approximately 16 bytes including padding, which is about 16 megabytes total. Union mixed with int I or double d has size 8 bytes, about 8 megabytes total. You save 50% memory, but you must keep track of which variant is valid, often via an extra enum flag, adding 1 byte per element, negligible compared to 8 bytes. The time penalty is the extra if or switch to decide which member is read. If you need simultaneous access to all fields, use struct. If only one representation is needed at any moment, and memory is critical, use union. If the data size is huge and cache pressure matters, prefer union because a smaller object fits more lines per cache block, reducing cache misses. If you frequently convert between representations, a struct may be cheaper because you avoid repeated conversion cost. Think of a Swiss Army knife union versus a toolbox struct. The knife gives you exactly one tool at a time, keeping the bundle lightweight. The toolbox holds many tools simultaneously, making it heavier but always ready. Understanding the memory layout of struct and union allows you to deliberately shape the space-time profile of your algorithm. Shrink the data structure when memory is the bottleneck, or keep multiple fields when speed of access outweighs memory cost. Determine alignment requirements typical 32-bit or 64-bit platform. Char aligns to 1 byte, short aligns to 2 bytes, int aligns to 4 bytes, double aligns to 8 bytes. Layout struct A, C1 at offset 0 size 1 byte. The next member int I requires 4 byte alignment, so 3 padding bytes are inserted and I starts at offset 4 occupying bytes 4 through 7. Char C2 requires 1 byte alignment placed at offset 8. Short S requires 2 byte alignment. Offset 9 is not a multiple of 2, so 1 padding byte is added and S starts at offset 10 covering bytes 10 and 11. The current size is 12 bytes. The largest alignment is 4. Rounding up to a multiple of 4 leaves 12. Therefore, the size of struct A is 12 bytes. Offsets are C1 equals 0, I equals 4, C2 equals 8, S equals 10. Union B size equals the size of its largest member, the maximum of 8, 12, and 1, which is 12 bytes. Its alignment is the maximum of 8, 4, and 1, which is 8 bytes, so the union is padded to the next multiple of 8, the next multiple after 12 is 16. Therefore, the size of union B is 16 bytes on a platform where double needs 8 byte alignment. If double only needed 4 byte alignment, the size would be 12 bytes. The hexadecimal constant 3, F80000 corresponds to the binary representation of the floating point, number 1.0, F. The union stores this bit pattern, so both members share the same 4 bytes. The print call therefore prints I equals 1065353216, which is the decimal value of the hexadecimal pattern, and F equals 1.00000. According to the C standard, accessing a union member different from the one most recently stored is implementation defined. Most compilers allow it as shown, but it is not strictly portable. Additionally, the strict aliasing rules treat this as a violation unless the program uses a character array or a mempb call to perform the conversion. Edge case analysis. On a big Endian platform, the same bit pattern still represents 1.0f, but the byte order in memory is reversed. The printed integer remains 1065353216 because the integer view follows the platform's Endianness. If the compiler adds padding before the union, such as when the union is a member of another struct, the offsets need to be recomputed using the offsetoff macro. The assignment b equals a copies the pointer value, so both a dot array and b dot array point to the same dynamically allocated memory. Changing b dot array at index 0 also changes a dot array at index 0 because they reference the same block. Consequently, a dot array contains 99, 1, 2. To perform a deep copy, allocate a new block for b dot array and copy the contents, for example using malloc for 3 integers and mempb to transfer the data. After this, modifications to b dot array no longer affect a dot array. Tip for students: always draw a memory diagram showing offsets, sizes, and padding before answering size-related questions. For union questions, remember the rule all members start at offset 0 and that the active member matters for reading values. 7.1 What is a bit field? A bit field is a way to declare an integer type member that occupies a specified number of bits, instead of the full width of the type. Struct flags open brace unsigned int :3 comment can hold values 0 to 7 close parenthesis unsigned int b:5 comment 0 to 31 unsigned int unnamed :2 comment unnamed only padding unsigned int c:1 comment single bit flag close brace semicolon. The colon followed by a constant expression :3 tells the compiler the field's width. The underlying type unsigned int only determines the allocation unit. The compiler packs fields together as tightly as the ABI permits. Why use them? Space efficiency. Storing many Boolean or small range values in separate ints wastes memory. Often 4 bytes each. Bit fields can shrink a group of 10 flags from 40 bytes to just 2 bytes. Direct mapping to hardware registers. Many microcontroller registers expose individual bits for control bit fields, let you write reg.enable equals 1 instead of masking shifting manually. Mathematical modeling. Certain problems, for example representing a set of numbers less than or equal to 31, can be modeled as a 32-bit mask. A bit field can hold the same information while giving named access. Example: RGB color packed into a 32-bit integer. Union color open brace struct open brace unsigned int blue:8 comment least significant byte unsigned int green:8 unsigned int red:8 unsigned int alpha:8 comment opacity close brace comp uint 32t value comment whole 32-bit word close brace semicolon. Union color call equals open brace.comp equals open brace.red equals 255 comma dot green equals 128 comma dot blue equals 64 comma dot alpha equals 255 close brace semicolon. Print open parenthesis quote hex equals 0x%08x backslash end quote comma call dot value close parenthesis semicolon comment prints ff8064ff. Alignment and portability notes. The order of bit fields is implementation defined. Most compilers place the first declared field at the least significant bits, but some put it at the most significant bits, especially on big Endian machines. The maximum width of a field cannot exceed the width of its underlying type. Unsigned int is often 32 bits, so :33 is illegal. Unnamed bit fields with width 0 force the next field to start at a new allocation unit, useful for aligning to hardware register boundaries. Mathematical expression of a bit field mask: if a field occupies W bits starting at position P0 equals LSB, the mask that isolates it is mask equals open parenthesis 1U shift left W close parenthesis -1 close parenthesis shift left P. For the red component in the previous example, W equals 8P equals 16 mask equals open parenthesis 1 shift left 8 close parenthesis -1 close parenthesis shift left 16 equals 00 FF0000. Reading the value programmatically without a union would be red equals open parenthesis call dot value ampersand mask close parenthesis shift right P semicolon. Real-world analogy: think of a parking lot with numbered spaces. Instead of having a separate ticket for each car struct members, you paint a tiny colored stripe on each spot bits. The whole lot can be represented by a single map, the underlying integer. You can check if a specific spot is occupied by looking at the corresponding stripe. When not to use them. When you need exact control over the layout across different compilers or architectures, manual masking is safer. If you require atomic updates of the whole word, bit fields may generate multiple machine instructions, making the operation slower. For networking protocols, where the bit order is defined by the standard, using explicit shift mask code often improves readability and portability. Type punning means interpreting the bits of a value of one type as another type. The classic C trick is a union with a float member F and a uint32t member U, initialized with F set to 3.14F. Then bits are obtained by reading the U member. The C standard says that reading a member other than the one most recently stored is implementation defined, not undefined. Most mainstream compilers such as GCC, Clang, and MSVC treat it as well-defined and generate the expected bit pattern. However, strict aliasing rules state that an object may be accessed only via pointer to its effective type, a character type, or a qualified version of its effective type. Accessing the same storage through a union violates the strict aliasing rule unless the union member is accessed through the union itself. Many compilers assume strict aliasing and may optimize away the read, producing wrong results. Safe alternatives are: first, use mempb to copy the bytes from the float to a uint32t variable. Second, use an unsigned char array and mempb to copy the bytes. Third, compile with the flag -f. No strict aliasing for GCC or Clang if you must keep the union trick. Uninitialized padding bytes. Padding added for alignment is indeterminate. Copying a struct with mempb or assigning it copies the padding bytes as well. If you later write the struct to a file or compare it with mempb, the result may differ between runs because the padding may contain leftover stack garbage. Fix is to zero initialize the struct. For example, struct ss equals open brace 0 close brace, or use memset with address of s 0 size of s before copying. Reading an inactive union member is implementation defined. Some platforms such as certain embedded DSPs may trap on such reads. Always keep a tag enumeration that records which member is currently valid. Define an enum kind with values intk and float k. Define a struct variant containing a kind field of type enum kind and a union with an int I and a float f named u. Access only the member that matches the kind. Violating alignment requirements. Forcibly casting a pointer to a misaligned type leads to undefined behavior on platforms that do not support unaligned accesses. For example, a character buffer of 5 bytes cast to an int pointer may be misaligned, and writing through that pointer is undefined behavior on many CPUs. The compiler may generate a fault or silently truncate the write. Use mempb to copy into the correctly aligned object, or use compiler-specific attributes such as aligned attribute with 4-byte alignment. Zero-size bit fields and packing. An unnamed bit field with width 0 forces the next field to start at a new allocation unit, but the exact boundary is implementation defined. Relying on a specific layout across compilers is unsafe. Example of undefined behavior caused by strict aliasing. A float variable f set to 1.0f, then an int pointer IP is obtained by casting the address of f, which violates strict aliasing. Storing the hexadecimal value 12345678 through IP is undefined behavior. The compiler may assume the float is never accessed through an int pointer and keep a cached copy, so the store through IP may be discarded. How to diagnose these pitfalls. Compile with warning flags wal, wextra, and w-strict aliasing equals 2 for GCC or Clang. The compiler will warn about many aliasing violations. Use static analysis tools such as Clang Tidy or Sonar Quebe that detect reads of inactive union members. Run under Valgrind or address sanitizer. They catch misaligned accesses and use of uninitialized memory. Bottom line checklist for safe use. First, always keep a tag for unions that can hold different types. Second, never read a union member that wasn't the last written unless you intentionally rely on implementation-defined behavior and the target compiler guarantees it. Third, avoid type punning via pointers. Prefer mempb or union access via the union object itself. Fourth, zero initialize structs to give deterministic values to padding bytes. Fifth, respect alignment. Do not cast an arbitrary character pointer to a larger type without ensuring proper alignment. Sixth, do not depend on bit field order for portable binary formats. Use explicit masks if exact layout matters. By following these rules, you stay within the defined part of the C language and avoid subtle hard-to-debug crashes that often appear only on certain compiler CPU combinations.